Okay, so this is the first of the recordings that we'll be making that are going to be describing a technical paper in some detail. We're going to try and keep it relatively short, 10 to 15 minutes, but it will be certainly a technical discussion, and we'll try and keep it quite conversational. As to why we're doing this, of course, publications are really the currency, how we communicate in research. And we feel that by having these short videos, it might increase accessibility of those publications, offer opportunities for additional engagement, and hopefully add some value as well to the community. In terms of what's next after this recording, we hope to make more recordings of journal papers in the future, and we of course welcome feedback on any thoughts that anyone has. Now, specifically, why this paper? So this is from the 18th World Conference in Earthquake Engineering. This is a paper that we presented, and it's a recent paper, of course. So that's one reason why this particular paper. But it's also about a topic that it's very, very near to my heart in terms of things that I've worked on for some time, and I believe it'll be useful to discuss some of the history of displacement-based design, some of the simplifications that we're considering, and how it could really be helpful for future code development. So with that introduction, we'll get right into it. So in terms of displacement-based design, I think this slide is really describes the procedure rather completely. It's an approach that utilizes an equivalent single degree of freedom system to represent a more complex multi-degree freedom system, such as a multi-story building or a multi-span bridge. It utilizes the substitute structure approach to define the nonlinearity of the system with equivalent properties of equivalent effective stiffness and equivalent damping. And through the combination of those parameters and the selection of a target displacement, we can define the base shear equation for displacement-based design, which you can see here in the right. So the expression allows you to determine the required strength for a system given the hazard, which is characterized by the response spectra with a corner point period and corner point displacement, so that point right there where the pointer is, and equivalent viscous damping, which depends upon the type of structural system. So now, in terms of a bit of history, I really think it's helpful to think about where these things come from. And I had the opportunity when I was a graduate student to work with Nigel Priestley, and these are some of the handwritten notes that were from one of our early meetings in 1993. And you can see in this handwritten sketch really the entire process. And it's really, I think, quite neat to look at this. You can see here's the response spectra that's been drawn out. Here we have that single degree freedom system. We have relationships here between ductility and damping. You see the calculation of the effective period by entering the response spectra with a displacement and reading across and down to get that effective period, and you intersect the appropriately damped response curve from the damping values here. And you convert that period into a stiffness and obtain the base shear. So in this little very simple handwritten sketch, it's really all there. In terms of what happened after that, again, discussing a bit of history, it was in I think really one of the more well-known papers that he wrote on myths and fallacies in earthquake engineering, conflicts between design and reality, where he laid out the direct displacement-based design approach. And I've got the key steps that are there. I won't read them. You can look at them there. But the important thing to note is that in the direct displacement-based design approach, what makes it direct is that we're starting with displacement, what it is we're trying to achieve, and when we end up with the required strength and stiffness. So we do not calculate period or stiffness at the start of the process. Rather, we choose the level of damage, the displacement we want to achieve, and we end up with the appropriate stiffness based upon the appropriate value of damping that is consistent with that target displacement. And this approach was first defined in this way by Nigel Priestley in this paper. So following that, there was an extensive amount of verification studies that were done over the years. And this included examples for bridges as well as buildings. You see here a couple examples for multi-span bridges with some irregularities, and as well as one that's quite symmetric. And the message from here is that you can choose the value of your target displacement or your target displacement profile, which you see in this example here. And when you execute the approach, you end up with a bridge that when subjected to that level of ground motion consistent with that hazard, you achieve the intended performance. So it's a procedure that allows you to achieve a particular level of performance characterized by your target displacement. So a very powerful tool for performance-based design. There are similar verification studies that have been done for buildings. You can see here a multi-story building frame, and you can see that the design target displacement profile is in blue. And you can see right below there, for both the 12 and 16-story building, you see the results of nonlinear time mystery analysis with records compatible with the target spectrum, indicating good agreement between the intended target and the resulting outcome of the design when subjected to that series of ground motions. So again, a very useful tool. So why am we talking about this now? Why is DDBD important within the context of, let's say, codes and future code developments? And we'll get more into that later. But what I want to introduce here is the force reduction drift paradox. And what we're talking about here is this. And if we take a multi-story building, shown as one shown here, we calculate the yield drift of such a structure. And given the, let's say, parameters of the length of the bay and height of the beam, typical for a multi-story building, in this case, we're getting a yield drift of about 0.8%. And if our limit state displacement is, let's say, defined by 2% drift, which is typical for most codes, for example, the US code, 2% drift would be typical. Our design ductility in this case would be around about 2.5, right? Somewhere in that range. Yet our force-based codes use a force reduction factor of 8 in the US. And immediately we see this problem, right? We see this incompatibility between drift limits and force reduction factors. We have a drift limit of 2%, a yield of about 0.8%, implying a ductility of about 2.5. Yet our building codes are suggesting a force reduction factor of 8. And it's that incompatibility which is really important and really something that needs to be addressed. And it's something that I think is a significant shortcoming of our current codes when we're trying to accomplish performance-based design. So now we want to talk about some of the simplifications, and we think that with some simplifications we can get a bit broader adoption. So this is now talking about some of the current things that we're working on. And if you look at this slide, you see here the relationships between damping and ductility, which have been well established using Jacobson's approach. They are shown here for different hysteretic systems. And for example, if we take the Takeda thin hysteretic response typical for a reinforced concrete bridge column, we can see here the relationship between damping and ductility, which is this black line here. Okay. Now, if we take that value of damping and we normalize it to the Takeda thin response. So now you see the values of damping on the left, and on the right, you see what we're calling the strength ratio. So damping relates to eventually strength using the displacement-based design Bayes shear equation. And if we determine what the strength is relative to the thin Takeda, we find something very interesting. So if you look at, for example, the large Takeda, which is green, or the elastoplastic, which is this dashed line, what you see is that irrespective of the value of ductility, that there isn't really a lot of change, meaning that for the large Takeda response, the values of strength are approximately 86% of what you get from thin Takeda. And for the elastoplastic, it's about 77%. For the flag shape, there's a bit more variation in the low ductility, but it's about 1.5 in round numbers, what you would get for the thin Takeda. That, of course, makes sense. The flag shape response has lower levels of damping. You expect there to require more strength. But the important thing from this figure is that we realize that irrespective of ductility, there's not a huge variation. So if you knew what the value of the strength is for the thin Takeda response, you could multiply it by the appropriate values to get the required strength for these other hysteretic systems. Now, if we normalize everything with respect to values of ductility, we also see something quite interesting, right? So now we take the same thing and normalize to ductility value of 4. And we see that irrespective of the hysteretic system, you get about the same ratio, meaning that the shape of the damping ductility curve is pretty much always the same. Of course, the values change, but the relative shape is the same, meaning that if you have the value of strength obtained for a ductility 4 design, the value at ductility 6 is going to be about 63% of that value, irrespective of which hysteretic system you choose. So that's also a very useful observation. And what this lets us do is to normalize everything to the thin Takeda ductility 4 choice. So if we normalize everything to thin Takeda displacement ductility of 4, we get this figure that we see up on the right. So by doing this, we can calculate a base shear for all systems. The DDBD base shear equation simplifies greatly, simplifies to this equation, which is a function of the hazard, which is the corner point displacement and corner point period, the yield displacement, and the effective mass. And that's it. So you can now design everything as if it were Takeda thin ductility 4. You get an answer, and then you adjust it based on these relative values. So if you get a value from this of 1,000 kilonewtons for your ductility 4 thin Takeda design, but what you really have is fat Takeda ductility 6, well, you multiply that 1,000 kilonewtons by 0.53, and that's your required strength. So I think a very simple way of making these changes.
And the other side of simplifications for DDBD, we have also have been looking at simplifying on the hazard representation side. So we're proposing some spectral simplifications. So let me remind you of what this means. So in 2014, Shahi and Baker did a study which essentially measured what the conversion factor is between rho D100 and rho D50. So now rho D100 represents the maximum of the peak values in the response spectra, and rho D50 is the median or 50% percentile of the peak values across all multiple directions of the ground motions. Another way of looking at this ratio is the inverse ratio of that. So essentially looking at how much of the amplitude of rho D50 is in proportion to the maximum. In that manner, we can look at any percentile of the peak amplitudes of design ground motions to the maximum, which is rho D100, that cannot be exceeded. So in this plot, we are summarizing the results of our sensitivity analysis using a suite of ground motions, and we're superimposing the Shahi and Baker study, which only looked at the rho D50 to rho D100 relationship. And in this case, you can see that the dashed gray line and the solid black line refers to two different tectonic regions that these ground motions that we use in our study belong to, and that they're right on top of each other, meaning that there is no impact from tectonic region affecting this proportion of any NN to rho D100. And as well, we didn't see an impact on damping ratio. So no matter if the design spectra is damped at 5% versus 15%, there is no significant variation. So we can use these conversion factors at any damping ratio and any tectonic region or type of ground motion signal. So as you can see here, our mean rho D50 to rho D100 ratio that we're calling ZNN, NN representing any percentile, is equal to 79% of the maximum, which is exactly the same as the average that Shahi and Baker found for rho D50, and the standard deviation matches quite well, given that they use more than 10,000 records and we use under 100 records for our study, which gives us good credibility, at least in this percentile. And you can see that as we decrease our percentile of the response, we have an increase in variability because the values start to look different. Those peak amplitudes start to look different. And above 50 until 100, we do see a decrease in that standard deviation. So what we're using these factors for is that we can then work with the rho D100 or the maximum response spectra for any particular location, for example, and using these ratios we can find any percentile that we might be interested in looking at in design. So in bridges currently we're using rho D50 in AASHTO in the US, and in the building community we're using rho D100. So this ratio allows you to go back and forth between 50 and rho D100 or anything in between if the designer likes to look at what would be the hazard at that point. So how we're connecting this to DDBD method. So in DDBD method, we entered our displacement spectra with a target design displacement or limit state displacement, and we identify our corresponding period. You can see here that from that period, we calculate our effective stiffness, and then we calculate our design base shear with that limit state displacement and corresponding stiffness. By similar triangles, we can see that given a linear displacement spectra, we can see that the base shear is directly proportional to the inverse of the square of the effective period. So with that relationship in mind, we can say that we can find the rho D100 base shear for the same structure limit state target displacement as a function of the rho DNN, in this case 50, times the ratio of the 100 to the 50 square. Moving this around so that our base shear of NENN is on the dependent variable side, we can see that the ratio of NENN to the maximum square becomes our DDBD strength ratio. So we can find any base shear value of NENN by knowing or having found our rho D100 base shear and multiplying that by the square of our ZNN conversion factor, and we have named this square of ZNN as VNN, or the DDBD strength ratio. In that case, with the DDBD strength ratio, again based on this linear design spectra, we can see that having calculated that for the same suite of motions that we saw, we have that at 50% for a design of rho D50, we would get 63% of the strength that we would get designing rho D100 for the same limit state displacement. And on the right, we can see the coefficient of variation of this DDBD strength ratio, and we see that for rho D50 above, we have a coefficient of variation less than 10%, and it does increase up to 35% if we look at the rho D00, which is the minimum peak amplitude. So this allows us to start with a design or a base design with the maximum, and then later look at what would be the strength required at any other NN. So going back to that same building example that Mervin presented earlier, we have our yield drift shown here, characteristics of the building. We calculate that to be 0.83%, and assuming an effective height of 70%, we found our yield displacement for the building, as well as assuming an effective mass of 70% of the total, we found our effective mass. So with these values, then we use that simplification that he introduced, accounting for the simplification of the dampen, and we calculate initially with our base strength, our baseline of ductility 4 for Takeda thin. As you can see here on the left, those relationships. But let's say we want to know what it is for other hysteresis rule. So what we do is go back in this graph and we identify what the values are at Takeda fat. And let's say we don't want ductility 4, we want to know what is at ductility 2, so we go up to the value of 2.2. We use that, multiply that by our baseline design, and we find that our Takeda fat ductility 2 design is actually of 978 versus 445 for a baseline design. So now, if we compare this baseline design of ductility to Takeda FAT to a full procedure DDBD, not using the simplifications, but just going through the full detailed procedure, we see that the difference is not that big. It's actually very close, and 1,000 versus 970, as you can see here. So all of these designs up to this point have been done using ROD100 design spectra. And if we compare that, again, using ROD100 to what it would be, what the design strength would be following the force-based design method with an R factor of 8, we actually see that is quite lower, or 60% of, about 65% of what our full DDBD is telling us that the design strength should be. And let's say that we don't want to design to ROD50, to ROD100, or the maximum response for this building. We know that perhaps the hazard is closer to the median of these peak amplitudes, or we want to know the range between the maximum and the median peak response. So we can use our VNN factor to multiply that strength that we obtain for Takeda FAT ductility 2, and we multiply that for the ROD50 case for 63%, and we find that it's about 616 kilonewtons for a ROD50 design. So that way the designer can know that at ROD50 you have 60% of what a ROD100 you will have for the same building. Other challenges in the DDBD that we're currently looking at, it's also the display shape. So in the case of transverse design of the bridges, there is the iterative nature of the procedure where we start with a guess of display shape, and then we conduct several iterations until this shape converges. So we're looking at simplifying this so that it's more broadly applied, or easy application of the method. And another thing that we mentioned is that those simplifications for the VNN, specifically the DDBD strength ratio, we did that in the basis of linear spectra, but we also want to see, we're looking at simplifying that, accounting for the multilinear nature of the design spectra currently in the new editions of the US standards. And it's different because depending on the location, the slope between these prescribed periods changes. And another thing that we're looking at, another aspect that we're trying to simplify to make practice more aware of what these choices are, ROD50 versus ROD100, it's also, could there be another percentile of the response that more adequately represents the solution space for a particular bridge? And to do that, we need to account not only the design and the principal directions of the bridge, but also in any off axis of the bridge. So for that evaluation of what ROD-DNN should be used in design, we need to look at the performance of bridges under multidirectional loading. And with that, thank you for your attention. Hopefully this was informative. So thank you. Part of this research was funded by Alaska DOT and conducted at the CFL Constructed Facilities Lab at NCSU. And this presentation was part of the World Conference in Earthquake Engineering this year in Milan. Thank you.